Welcome everybody and welcome here. We have people in the room because a workshop at the GGI is running on randomness, integrability, and and universality. Thank you, Filippo, the organizer of the workshop. And it's a pleasure to have this GGI Tea Break here in our room. That means that we are going back to the in-person activity, and we are very happy. So I thank the speaker, Tomaz Prosen, to accept to give this seminar. And the title is Exactly Solved Models in Many-Body Quantum Chaos. But before starting, I leave Alessandro to introduce you. Thank you.
Thank you very much, Stefania, and thank you to everybody who managed to join in person in Florence, and also to the colleagues that joined us as usual on Zoom. This is indeed a very special occasion because we have the possibility of having a dual talk, and that's really a great synergy with the very nice workshop that Stefania mentioned on randomness, integrability, and universality. So we are very glad of that. Let me just say a few words about Tomaz, who of course is a world-renowned expert in the field of exactly solvable models, integrable models, and many related topics like transports, quantum systems, quantum spin chains, and indeed quantum chaos. Tomaz got his PhD in Ljubljana, and after some postdoctoral stays, did most of his career in Ljubljana, where he's now full professor and the head of the group on non-equilibrium quantum and statistical physics. His research has been hugely impactful and among other things has been awarded a prestigious ERC advanced grant, which, as you see from the slide, actually sponsors some of this research that we are going to hear about today. And it covers many topics in the theory of integrable models, in the theory of spin chains, transports. In particular, one strand of the research that Tomaz has been working on has to do with a very interesting topic, which is quantum chaos. This is, of course, in a sense, an old topic that has been interesting for years, but that lately has led to very interesting new ideas and new discoveries that can be of interest, I believe, both in the field of condensed matter physics, mathematical physics, but also in the field of high energy physics, where some ideas of quantum chaos are now receiving finally attention. So I think that this colloquium will be, I believe, very interesting for physicists of all backgrounds, and I personally look forward very much to it. I just have a little bit of housekeeping. I think it will be particularly tricky if there are questions during the talk, especially in the room, because I don't think we will hear them unless people have a microphone. So if there are urgent questions and they are in the room, I think Tomaz should probably repeat them. Otherwise, probably it's best to defer all the questions towards the end of the talk. This being said, I finally leave the floor to Tomaz. Please take it away.
Thank you, Alessandro. Thank you for inviting me to give this talk here. So it's also nice to give it in front of the audience. So since you mentioned, I mean, this is basically, well, I hope it will be enough colloquium style talk for the general audience, but it's basically a talk about a recent progress or recent line of research, which was mainly, well, at least big part of this research has been done in our group, and it would not be made possible if for the ERC project that Alessandro mentioned. In particular, I would not have been able to hire such excellent postdoc, for example, as Bruno Bertini, and also Pavel Kos did his PhD, which was basically fully covered by ERC grants. So actually, these are the two heroes which I want to mention, which were mainly responsible for the, let's say, for our group contributions to this thread of research. And also, I would like to spend maybe a couple of minutes to motivate why I'm personally interested in quantum many-body chaos, and also a little bit on the history of the problem, which will also be going to be, I mean, which I'm also going to kind of describe in a couple of slides later on. but you see, I mean, I understand that, you know, I mean, okay, this is kind of a new subject now. I mean, many people, it's a new subject. For people like me, it's an old subject because it was basically, at least the quantum chaos of single particle problems was the field through which I entered science back in the old days of 1990s. And in those years, and also these years, I mean, if you teach dynamical systems and chaos or Hamiltonian chaos to students, basically you use very simple models. Yeah, I mean, I tried to write this title on the first slide of my talk, which is the goal of this endeavor, which is to find, I would put in quote, Baker and Cat maps of many-body quantum physics. Namely, if you teach kind of the, let's say, Hamiltonian chaos, sometimes I would use these two words, quantum chaos and Hamiltonian chaos, by referring to, let's say, the classical counterpart of quantum chaos, Hamiltonian chaos, or Lyapunov chaos, if you want. But there are these caricature models, I mentioned, Baker maps, Cat maps, which are so easy that you can solve them on the blackboard. You can compute correlation functions analytically. I mean, these models, maps on a torus, Cat maps, or Baker map, again, which is a linear map with some discontinuity lines, but still, you can compute, you can define this map on function spaces, and then you can write them in terms of linear operators, like transfer operators. You can diagonalize those transfer operators. You can find correlation functions. So this has been kind of since decades ago. And, you know, when I tried to enter, it was like, you know, for me, it was many-body physics was more like a hobby in the first years of my career. And I do something for many-bodies. I mean, you start to learn many-body physics, then you see, okay, not much can be done. I mean, there is lots of, very complicated perturbative methods, but, you know, there's very little that can be done really in describing dynamics, apart from free systems, but free systems are really very special. Then you go to integrable systems. They are also very special. Of course, much more generic than free systems, but still you cannot do much. And then you try to really think, I mean, are there models which are like not free, not integrable, on the other end of the spectrum, fully chaotic, but still amenable to exact solutions? So my talk is about that. It's about trying to find models which are simple enough so that we can solve them analytically, but, you know, not, I mean, since they are chaotic, you cannot really solve them. Like, you cannot, well, there are no trajectories here, but as you will see, I mean, what I will speak about will be exact solutions in the sense of statistical mechanics. So we can solve correlation functions. We can describe energy spectral statistics of these models, things like that. So, okay, but now let me go back to the history a little bit and, well, at least see what were their driving ideas, which kind of were there in the beginning of this field. And one of the most kind of one of the strongest ideas were this conjecture, which I will refer to as quantum chaos conjecture, because I will understand it in a bit more abstract way. But originally, this idea has been phrased as Bohiga's conjecture or Bohiga's Giannoni-Schmidt conjecture. Why I'm trying to use make a slight distinction, because as I say, I mean, I will try to use it generally in systems which don't necessarily have a classical limit. But the idea itself has been formulated for systems like this, billiards. So systems which, Hamiltonian systems which have classical limit and which you quantize. And then you ask, can I understand the energy spectrum of these systems, let's say in statistical sense? So thinking of energy spectrum as a gas in 1D, can the statistics, endpoint functions of this gas be described universally? I mean, and yes, this was the pioneering idea of Bohigas, suggesting that it was motivated, again, similar as Wigner's proposal of random matrices in physics. He was motivated in nuclear data ensemble, in nuclear physics data. So, but, you know, these are complicated systems, nuclei, but these models are very simple. So the idea was what is really important to describe universally spectral statistics of these models. And the proposal was that what is important is chaos. So Hamiltonian chaos. So the fact that underlying classical ray dynamics is chaotic should be enough to justify the applicability of random matrix theory in describing statistics of levels. So these are typical plots that you would see in dozens of papers in beginning from 1990s. People were diagonalizing Laplacians characterized by domains which were the shape of a circle or a chaotic billiard, and then they would analyze spectral statistics the most popular measure would be simply the distribution of level spacings. And then for chaotic systems, there was this proposal or conjecture that level spacing should be described by what is referred to as Wigner's matrix. So random matrix, well, Wigner's matrix was even simplified random matrix theory, which was like 2x2 matrices. So even if you just look at 2x2 matrices, assuming that the Gaussian that elements of 2x2 Hermitian matrices would be IID Gaussian random, the level spacing would excellently describe level spacings of chaotic of systems which have chaotic classical limit. If you want to do this more accurately, of course, you use n by n or infinity dimensional random matrices, but still, I mean, it should be already, I mean, as you probably understand that even in those days, it was kind of very exciting. Conjecture could be true because on one hand, you have very structured models like billiards, Laplacians on well-defined simple geometries, and you relay those spectra, let's say, frequencies of the drums on which you hit. I mean, this has nothing to do with quantum mechanics, right? This is wave mechanics. So you take a resonator, you excite the resonator, you measure the spectrum, and that spectrum should be given in terms of eigenvalues of random matrices. So that was a very powerful idea. And the question is, could you prove such an idea? And I will go a little bit into that, but let me just now describe my favorite measure with which we will measure validity of random matrix theory. The simplest measure, namely, we could, of course, use these level spacings, which are very popular, but this is very difficult for a theoretician or a mathematical physicist to describe because it's a multi-point measure. So there is some echo here. I do hope I don't have, no, I don't have my, I think it's okay. I hear myself through the computer, but I think I'm muted, so I think there is no echo really. Okay, so what I want to describe, I mean, the measure I want to define is a two-point function. It's a pure two-point function. So it's a basically, so what you do now, you consider an evolution operator and the spectrum of evolution operator, right? And okay, there's one other point which I skipped in the first slide, but this Buchiga's conjecture should also be applicable to periodically driven systems. And I like very much periodically driven systems because there you could consider time to be discrete. So these are maps. So instead of Hamiltonians, you use maps. Instead of Hermitian operators, you look at unitary evolutions. I mean, that in some sense is more abstract than Hamiltonian, but it's just as good as Hamiltonian. So instead of looking at spectra of Hamiltonians, we will look at spectra of periodically driven systems, so that spectra of this evolution operator, the Floquet operators, the unitaries. And I will name this spectra phi of n, and let's now consider the simplest two-point function. A one-point function is supposed to be trivial. We assume that the spectrum has some flat density. So this would be a spectral density, of course, before you average over the ensemble of whatever. So it's still a straight train of delta function. And then you define a two-point function, right? And you average this two-point function with respect to the center with a fixed distance theta. You integrate over the center. So this would be for a fixed spectrum a two-point function. Then you do a Fourier transform of this two-point function. And then the two-line calculation tells you that this is just trace of the evolution operator to power t modulo square. So this is a two-point measure, right? So it's given in terms of two replicas of the evolution operator. So two trace object. Again, I mean, this is something that if you don't believe me, I invite you to do it after the talk. I mean, it's really, I don't want to do really calculations in this talk because, you know, I want to go more superficially through many different results and ideas, but, you know, it's something very easy to check. Okay, now, of course, there is another problem with this object, that it doesn't really exist. I mean, if you compute it for a many-body system or for a system which has a lot of, where Hilbert space has a lot of, I mean, has high dimension, then you compute this k of t and you find that this k of t is all over the place. It doesn't really exist. I mean, the fluctuations of this object are of the order of the average. So what you have to do, you have to do this. I mean, the people in random matrix theory would tell you that this object is not self-averaging. So you have to introduce an ensemble of models, and then you have to average over this ensemble of models. So now, if you have a random matrix theory, that's easy because you have a Haar measure on the, let's say, unitary group. If you define unitary matrices as your random matrices, but in dynamical systems, that's more hard. I mean, you have to take some innocent parameter like magnetic field, and you average over this parameter to make this object well defined. Okay, and then let's see what random matrix theory tells us about this. So this object is called spectral form factor, and this will be the first part. Let's say third of my or half of my talk will be the main object that we'll consider, and let's see what random matrix theory tells us about this object. So this is basically, as I tell you already, I mean, this is a Fourier transform of the 2-point function. So it's basically, and we started with this level spacings. So level spacings it's not a pure point function, but the main contribution to level spacings is 2-point function. So it's basically a kind of Fourier transform of spacings. So you should consider now that a variable now is a Fourier variable to quasi energy. So time, right? So level spacing corresponds to mean level spacing, which is 2 pi over number of levels, which means that this corresponds to Fourier variable, which is of order of n number of levels. So now, if you get what random matrix theory tells you, so that means that this form factor, I mean, this is what you find if you compute this for random matrices, that form factor grows linearly, or grows somehow linearly in the beginning, and then it saturates to a value at time, which is of the order of mean level spacing. Number of levels, so inverse mean level spacing. So this is the so-called Heisenberg time. After Heisenberg time, then the spectral form factor saturates. And you can understand this, again, this is trace of the u to the t modulo square here. I'm sorry, the t is missing, the time should depend on time. So this double trace can be written in terms of a double sum over all eigenvalues. So see, I mean, you have to calculate this object, but when time exceeds the mean level spacing, then these are pseudo-random. These phases are all pseudo-random. So then this is easy. I mean, this is like n square objects, which are all pseudo-random, so it should be of order n. So this should saturate. Yeah. So this happens after a long time. After a long time, things should be flat. At short time, what you see is level correlations. And these level correlations, which now many people discuss, in particular also in holography, people who do quantum chaos in holography, I mean, are also interested in this. But I mean, this is really a strong signature of quantum chaos, because if you compare it to a spectrum which comes from a regular integrable system, then the spectral form factor should be flat. For example, if the eigenvalues are not correlated, and this is another conjecture, which goes under the name Berry-Tabor conjecture, which is also very old. I mean, it actually is even older than Bohiga's conjecture from 1970s. Berry-Tabor suggested that integrable systems should be described by Poisson sequence. So energies of integrable systems should behave like Poisson sequence. So that's reversal result on form factor, which should be flat independent of time. So see, I mean, now if you have a many body system, this time scale is exponentially long. So, and then you have a huge exponential gap between a ramp of a chaotic system and a plateau of an integrable system. So there is a really, this correlation pole really gives you a lot of room, and it's very easy to distinguish chaotic from regular dynamics. Of course, one should be careful. I mean, there is another time scale that people need to discuss, and they do discuss in this business, the so-called Ehrenfest time or Thouless time. So there is a time after which, only after which you can expect validity of matrices to describe your spectral form factor. So I will discuss a little bit this later on, but I just warn you, I mean, that is a time scale. In semi-classical system, time scale is usually related to log. I don't know what's happening. Okay, so now let me just give you one slide history on discussing this object. I mean, this has been really probably the main result of quantum chaos in the 1980s and 1990s, was trying to derive spectral form factor from random matrix theory. I mean, since Bohiga's conjecture, people believed that this could be, but it was not so easy. I mean, it was quite a tour de force result. It started with the first step, which was done by Michael Berry in '85, which is the so-called diagonal approximation. So the idea now is to take a semi-classical system which has an h-bar parameter and which you can take arbitrarily small. So it's like a billiard. In billiard, you can take highly excited eigenvalues, which means that effectively, since you are looking at energies which are, I mean, P times Q as much larger than h-bar, So the effective Planck constant becomes arbitrarily small. So if you go to, let's say, semi-classical regime, you could think of trace of u to the t as you could expand it again using Feynman path integral, and or some people now then refer to the methodology which was developed by Martin Gutzwiller, so-called Gutzwiller trace formula. So trace of the propagators can be expressed in terms of sums over classical orbits. These are like saddle point approximation to Feynman path integral, and these orbits have to be periodic because you take the trace. So trace of u to the t means you have to have orbits which go from the same point in phase space back to the same point, and then you integrate over the initial point. So basically you pick up the saddle points, and the saddle points are just periodic orbits. Now, but since this is a two-point object, there are two replicas, trace of u to the t times trace of u to the t conjugate. It's a double sum. And now this double sum has, terms which have oscillate widely, but if you pick terms, pairs of terms for which this phase is compensating this phase, which means for which action, pairs of orbits which have the same action, then these pairs of terms compensate. So you have the cancellation, right? So this is, it's a very intuitive idea, which was proposed by Michael Berry, which is called the diagonal approximation. So after you pick up only diagonal contributions, you get only positive terms. And then there is another kind of very general classical mechanical Hamiltonian geometrical, if you want, observation, which is known as Osorio de Almeida-Hanay sum rule, which gives you that this sum over all periodic orbits should be equal to the period of the orbit. So these are all orbits of fixed period t, and this should be given to be as a period of the orbit. So this is, this follows simply from, let's say, ergodicity, if you want. Now there is this factor of 2, which can be there or not, and namely this factor of 2 has to do with time reversal. So if there is time reversal symmetry, then there is always a pair of orbit which has the same action as a fixed orbit. So you can always pair orbit with itself or with its time reverse partner, and this gives this factor of 2. So if you go back to the prediction of random matrices, you see I didn't comment on that, but for systems which have time reversal symmetry, there is this circular orthogonal ensemble result which you should apply, which has a slope which is 2 times t. So for systems with time reversal, you have this result. For systems without time reversal, you have simply linear ramp. And now going back to this Berry's argument, this too can be easily understood. But then there has been much more, of course, afterwards. This was just a leading order, and people were wondering whether one can derive these two orders. And then people had to wait like almost 2 decades before the next order came, which was a result by Martin Sieber and Klaus Richter. And this was coming from, again, doing carefully the bookkeeping of cell points of Feynman path integral, but now you had to include terms separately terms of orbits which experience the so-called self-encounters. And moreover, if you go further, this gives you exactly the second order contribution. Namely, if you look at, again, random matrix result, random matrix result has, you can expand this in power series in T, and the second order is exactly given in terms of, correctly summing for all possible orbits which have these self-encounters. It turns out that these orbits now have more symmetric pairs, right? Because you can have an orbit which goes around number 8 in this way, or it goes along number 8 in the other way. So there are two, let's say there are 4 orbits. There is a prefactor 4 in the next, if you do Taylor expansion, the second order has prefactor 4 because it means that to each orbit there is a time reversal, but then there is a two possible rewiring or reconfigurations of this number 8. So then again, one had to wait further until PhD thesis of Sebastian Miller, who basically found then the complete kind of consistent resummation of all possible terms, which all possible kind of rewirings. This it was simply like, again, careful bookkeeping of its permutation symmetry with respect to rewirings, which resulted in precisely the random matrix result. Okay, now this was history. Now let's go to the main point of my talk, which is, and I will now have to do a disclaimer immediately. What I'm interested now are many-body systems, and not all many-body systems, but systems which have not small h bar, because many-body physics you can take thermodynamic limit. You don't have to take semi-classical limit. So you can have h bar, which is not a small number. For example, for fermions, spins 1/2, h bar is always of order 1 number. So I would immediately exclude discussions of large N QFTs or small h bar many-body systems. So I can do no saddle points, and there is no Lyapunov chaos. So this is just a disclaimer. I will not talk about autocs, for example. I mean, there's been a lot of development, again, mainly from the holography community, where people discussed this Lyapunov chaos, which was very interesting, but this is just a disclaimer. I'm not going to touch that. So what rather instead I will do, I will discuss systems like this one. For example, fermionic models or spin 1/2 models with local interactions. I mean, again, these models have been around in the literature since early 1990s, and people have looked at spectral statistics, and this was like a working indicator of integrability or the so-called quantum chaos. So people were calling these models chaotic as soon as they found level spacings which were random matrix, which were Wigner Dyson. I mean, I was always kind of annoyed by this, because I don't know why people refer to this in the 1990s and 2000s quantum chaotic, because there's no chaos, right? No Lyapunov exponents, no orbits, no instability. So what is it? I mean, these models apparently are described excellently by random matrices, but why is that? Because if you look at this many-body Hamiltonian, I mean, you can write it in Fock basis, which is exponentially large, but this model, this Hamiltonian, is hugely sparse matrix. It has only of log Hilbert space dimension, which is number of fermions, non-zero elements in each row. So there is kind of adjacency matrix, and it only has log n, where n is 2 to the L, non-vanishing elements in each row. Moreover, these elements are by far not random, but they are given in terms of, for example, in this case, 4 distinct reals, right? 4 coupling or interaction parameters, JJ prime, VV prime. So as soon as you have non-zero prime parameters, this model is not integrable, and you get spectral statistics, which is excellently described by random matrices. So this was the question which puzzled me for, I would say, quarter of a century. And I'm very happy that in the couple of years ago, beginning in 2017, 2018, we were able to provide sort of first kind of analytical understanding of these properties. So why is this model? Why are these spectra of these Hamiltonians described by random matrices? Okay, so now let's just to show you how this goes. I mean, I will again give you an old result of a paper of ours together with, at that time, a PhD student who I co-supervised, Carlos Pineda from Mexico. And we just looked at that time this model, which I will discuss a little bit more on in my later slides. This kick teasing chain, it turns out to be a kind of nice model because it's very simple, but still it's chaotic. So for example, in 2007, we have pushed the computers that we had at the time to the limit, and we computed the spectrum of spin chain of 19 spins. And we computed the spectral form factor. I call it K2 now. It's just the same form factor that I introduced in my first slides. And you see, this is what you get. This black sand, this is what you get if you don't do anything. So that's an object which I say it does not really exist. But then what you do, you simply average this object. Let's say this was just moving time average over, this was system of size 2 to the 19. So there is a couple of 10,000 levels in each momentum block. This system is periodically translation invariant, it's periodic. So you can take, you can bin it to sectors with fixed quasi-momentum. And in each quasi-momentum sector is still a couple of tens of thousand levels. So it's enough. I mean, so that Heisenberg time is of the order of 30,000. So you bin it to times, let's say, of 100 consecutive steps. Of course, maybe I forgot this, but my time is always an integer multiplet of Floquet period. So it's an integer. So 100 means something, it's 100 revolutions. So we bin this to, let's say, bins of 100 time steps, and then what we get is these smooth curves. So these different symbols are different quasi-momentum sectors. If on top of that you average over quasi-momentum, you get this black curve, and this excellently fall on top of the red curve, which is a random matrix result. So this is just, again, the numerical demonstrations from 15 years ago, that this really goes very well, so that random matrix theory really describes kicked models, I mean, the periodically driven models with very simple interactions. And then, okay, I will just mention a couple of papers that were kind of, I think the first which kind of addressed the problem of many-body chaos in this context, the spectral statistics in many-body systems, which are not the papers, which are not the results I'm going to talk about later, because I'm going to talk about maybe even cleaner result. But these were like the first sort of, I would say, announced results. One was from our group, which was about, again, a similar kind of model, Teasing model, but with long-range interactions, which are easier to treat in some sense. And then there was another approach from Oxford, from a group of John Chalker, who considered, again, Floquet systems, but with random couplings and with large local Hilbert space dimension. So large Q or large J spins, for example, I mean, where they could again do analytical calculations. So, I mean, the results seem to be true even for not so large Q, but to do analytical calculations, they had to take large Q, so large local Hilbert space dimension. So it's more or less like a small H bar result, but for a many-body system. In those cases, we were able, or people were able to kind of derive expected form factor. These results were asymptotic, and these results were not rigorous. So these were like, to me, it's kind of preliminary, but now let me just describe a rigorous result, a line of research where we kind of try to approach this problem rigorously and on a more restricted context, in a more restricted setting of nearest neighbor interactions. So what can we say about, let's say, spin 1/2 chains with strictly local interactions? So I will introduce now this Teasing model as the simplest model of this type, which is, again, an Ising model with nearest neighbor coupling in 1D plus longitudinal fields, which you put together, let's say, with the coupling because they're all commuting, right? Sigma Z, they're all commuting. And then on top of that, you kick it, which means you do it with in pulsed fashion. So first you take a free system, and then, let's say, with delta pulses, you kick it with the transverse field. So it's a free longitudinal system which kicked the transverse field. And for convenience, we assume that the longitudinal fields are random. They might have some disorder, but transverse fields are constant. This is for convenience. So this model is integrable only if the longitudinal fields are 0 or the transverse fields are 0. If both are there, this model is not integrable, even though it's probably the simplest non-integrable many-body system. Okay, and now how do we do disorder averaging? So now, as I mentioned right in the beginning, we have to do some sort of disorder averaging. So, so now, you know, that this is the reason why I picked this longitudinal field as position dependent, because now I will assume that this, sorry, it's a bit, yeah, okay, like this. So, so what we assume now is that this Hj are IID, which are let's say Gaussian distributed. So there is some average value of the longitudinal field, which I take as H bar, H average, and the variance, which I call sigma. So this would be like the object I want to calculate, right? This is the trace of u to the t square, but then I average over random fields. And if you just play a little bit with numerics, then this is what you get. So this is for a system of 15 spins, where Heisenberg time is 2 to the 15, which is somewhere far at the back of the room. But if you look at just the first, let's say 5–7% of the Heisenberg time, you get perfect linear ramp. Yeah. And then if you zoom up, zoom in at very short times, you again get something which is perfectly linear. But then there is some oscillations of fluctuations which become smaller the larger sigma you take. So the more averaging you take, the smaller fluctuations. But it turns out that these fluctuations go down even by increasing system size. So when you go to thermodynamic limit, fluctuations go down, and this becomes well defined. And it turns out that you don't need any, I mean, that infinitesimal is enough to make this object well defined. So that's kind of really a nice feature of this object, is that, I mean, this is a disordered system, but it, you know, it is immediately, if you want, ergodic. There is no localization transition. I mean, there is infinitesimal disorder, which is enough to make it ergodic. And the reason for that is that we take special values of coupling count parameters, J and B, which are pi/4. Of course,
I have another question.
Yes, it's a question.
So this KT is the spectral form factor, right? I mean, it's the
right.
Random,
that's spectral form factor.
Yeah. So where does the dependence on the H come in? Because the spectral form factor is just the density correlator, right? I mean, the spectral density. So where does the H come in the densities?
H, magnetic field.
Yeah. Magnetic fields, yeah.
Magnetic field is a parameter in the Hamiltonian. It's simply the parameter over which we average.
Yeah.
So this influences the evolution operator. So you have different spectrum for different H. So then you average over H.
Okay, good.
Yeah. Okay, so now the question is, can we prove this result? I mean, we are like trying to find now the simplest case which we can prove, right? And the answer is yes. This result we can prove if and only if we take these values of coupling constants equal to pi over 4. So this is a special point of Teasing model, which is referred to as self-dual point. And I will try to argue why is this kind of especially nice. It has to do with the property which later we called dual-unitarity or double-unitarity. So this is what we can prove. It's a very, let's say, small result still, but we liked it really well. I mean, it was really kind of excitement once we were able to get it. So for odd times, we can only prove it for odd times. There is some interesting number theoretic games there. I mean, for even times, things are much harder. For odd times, it's easier, but still we believe they are true also for even times, but then we can only conjecture it. So for odd times, we prove that the average, this K bar means disorder average over longitudinal fields, where the result is independent of the strength of disorder and of the average of the field. We find that the spectral form factor is 2t for times large enough. So there is no tauless time. So tauless time is of order 1 if you want. So this model is kind of behaving like random matrix theory at all time scales. And of course, we have to do thermodynamic limit, which means that Heisenberg time moves to infinity. So this result means that this model in thermodynamic limit is a kind of a critical chaotic system. There is no shortest time scale. There is no long scale. At all times, it behaves like random matrix theory. Of course, this is a very mild result still because it's just a 2-point function, and it's thermodynamic limit taken first. So, okay, so now this is just, maybe I should move on because I want to discuss a couple of other things which are even more exciting. But I just want to start with something which was kind of chronologically the first, and also it's probably the easiest or the simplest model that you can think of. And now, what is the main idea how to show these results? Again, it's an idea which is very kind of stat-mecky, if you want. The idea is to write the propagator, I mean, the trace of the propagator powered t as a partition sum, as a complex weight partition sum of a 2D statistical model. So this trace of u to the t of Teasing is, I mean, I will not go further into details of this, but it's easy to imagine. This is just like a partition sum of a 2D actually it's exactly 2D Ising model. It's a 2D Ising model with complex weights and with 2D magnetic fields, which are constant in space and constant in time. Now, in this case, time goes horizontally and space vertically, which is different than in the other slides. I'm sorry for that. But if you imagine now time is horizontal, so this would be constant time. So, and this would be constant space. So these are different random fields equal in space, IID in different space points, but constant in time. So this is a non-integrable 2D classical Ising model with striped random fields. And the idea now is to contract this partition sum not along rows, but along columns. So first we do it along rows, which is just a propagator, but then we do it along columns. Vice versa. First we did it along columns, which was just a propagator, right? This is just a UKI, is just a propagator. But then we do it along rows. But in rows, what is nice is that magnetic field is IID, so we can average over magnetic field after doing that. So there is this duality relation, which is simply like contracting partition sum either via row or column transfer matrices. But transfer matrices depend particularly on space point. But since the magnetic field in each space point is IID, so we can average over it. Before averaging, of course, we have to consider two replicas. I will not do it in this slide, but I will do it slightly more generally later on when we will consider more general setup. But this is kind of remarkable. I mean, I think we should now be kind of still already kind of excited because this unitarity of the dual evolutions, that double unitarity, namely that the transfer matrices can be unitary in both directions. I mean, this can happen in particular in the special points j equal to b equal to pi over 4. I mean, this of course is not in general. So the space evolution, this, what I call U tilde, this operator, for this model in particular, has exactly the same algebraic form. So it's again of the form of Teasing model, but for different coupling constants. I call them J tilde and B tilde. But J tilde and B tilde are in general complex, but they become real exactly when J is equal to B and absolute value equal to pi over 4. So at special points, the so-called self-dual points, both of these solutions are unitary. And this buys us a lot. I mean, this unitarity of this transverse evolution is something that really allows us to proceed and to do stuff. But I mean, let me just now go a little bit. Yeah, there is a time. Okay, so should probably seem like at least 20 minutes, right? So let me just now try to generalize this and provide with the more general class of models which share similar properties. And these models have been called dual-unitary models, and we will formulate these models as quantum circuits. So all these spin chains with nearest neighbor interactions, I mean, they can be, you know, at least after you do the Trotter approximation, they can be coded, if you want, quantum simulated as quantum circuits with local gates. Now let's consider now a simplest situation when you have local gates, which you then put next to each other, like in a brickwork fashion. And now let's just assume that these gates have the following feature. They map states ij to states kl. And now from now on, my time will always be vertical, space will be horizontal. So ij to kl is a unitary, but now what I ask is also that ik to jl is unitary. So there is a special flip, which I call tilde, reshuffling of indices of this 2 on 2, 2 qubit on 2 qubit, or 2 qubit on 2 qubit gate. And I ask that both of these guys are unitary, so vertical and horizontal. This is a very special constraint. Of course, this guy has to be unitary, but the transverse guy does not need to be unitary. So the question is, how fine-tuned is this choice? I will try to convince you later that it is not very fine-tuned, maybe less than you would expect naively, but still, of course, it's fine-tuned. I mean, this is measure 0 of all possible unitaries have this property that also the reshuffling is unitary. Okay, but this is something that we require, and this is what allows exact solution. So this is our quantum many-body cat maps, if you want, models which can be written as circuits with these double unitarity conditions. Now let me describe you in kind of sketchy and in pictures ways how for models like this, how for circuits like this, we can compute stuff. First of all, how we can compute again spectral form factor, and then how we can compute correlation functions, operator entropies, and things like that. Okay, so right, so now this would be like a general circuit, which I will now build from bricks, right, these red bricks, which each of these bricks is double unitary or dual unitary. So now this thing could be now understood as a many-body circuit which propagates 12 qubits for 4 half periods, so 2 full periods in time. But on the other hand, this could also be understood as a model which propagates 4 qubits for 6 full time steps, or 12 half time steps in time. So there is obviously this kind of a dual circuit, which I will call U tilde, which propagates horizontally, and then there is this duality of traces. And what is remarkable now is that both of these propagators are unitary. Now, why is this remarkable? Okay, now before going further, I will just convince you that, I'm sorry, maybe this slide should be put somewhere later, but anyway, let me just clarify how I can classify all these dual unitaries for qubits. So for most of our ideas and implications, we'll consider qubits, so d equal to 2. And for qubits, we can easily characterize this set of unitary gates, 2 on 2 unitary gates, which are unitary in both directions. So what actually happens, and again, this is a kind of calculation that you can do, maybe not in 5 minutes, but in 20 minutes. I mean, you just pick up the reference, which will tell you that any unitary on 2 qubits can be parameterized like tensor product of 2 SU2s to 2 by 2 SU2s, another tensor product of 2 by 2s, 2 by 2 SU2s, and in the middle you have the Heisenberg gate. So Heisenberg gate has 3 parameters, JX, JY, and JZ. And these guys have each 3 parameters, so it's 12 plus 3 is 15 plus 1, which is the overall phase, which is 16 parameters, which give you the SU4 or U4, unitary gate on 2 qubits. But if you take 2 out of these 3 Heisenberg parameters to pi over 4, then you can show that this gate is dual unitary. So it's a manifold which has codimension 2 in U4 in this case. So there are just 2 parameters that you have to fine tune in order to get dual. And there are many simple examples, like the simplest example would be a swap gate. Slightly less simple example would be a 6-vertex model in particular line of parameters, right? This would be just a 6-vertex R matrix if you want, but for particular value of parameters, which then would give you the trotterized XXZ chain for particular value of trotter time. And then there is this self-dual Teasing model that we discussed in the beginning of my talk, which can again be written as a circuit in terms of this gate with parameter j equal to 0. So this j, this is the essential coupling parameter, and the smaller it is, the more chaotic the model is. So this model, this is a kind of a, actually it can be, this parameter j can be related to what is known as entangling power of this 2-on-2 gate. And the smaller the j, the larger the entangling power. So j equal to 0 is the most entangling gate. And j equal to pi over 4, which is the least entangled gate, the no entangling gate, which is a swap. And this has been generalized. I mean, this kind of parameterizations have been generalized in a couple of papers, in particular by Austin Landcraft and Peter Claes. But then there are some other ideas with generalized Teasing model, higher D, and we're not going to that. But okay, but now let me just give you one slide on how now we can actually compute form factor. Sorry, there's some problem. Okay. Spectral form factor now for general dual unitary circuits. So if you take dual unitary circuit, which you build out of brickwork structure, right, in terms of two qubit dual unitary gates, and then you decorate them with single qubit gates, which represent random fields. So these bluish gates are random fields, and these red gates are constant, positionally independent dual unitary gates. So it turns out that the entire circuit is dual unitary, because single qubit gates are always by construction dual unitary, and you can read this evolution like this way or that way. And then you see the spectral form factor now is the expectation value with respect to this random fields of this double replica 2-trace object, right? Trace of u to the t, trace of u to the t dagger. And this is object like this. So it's just periodic boundary conditions in time, 2 replicas. One is complex conjugate, so one has forward gates, one has backward gates, and then you take expectation value. And now you see why this space-time duality trick is so useful, because now in order to evaluate this disorder average, now you can use it, because instead of doing it time-wise, you can do it space-wise. And if you do it space-wise, you can use the fact that disorder is IID. So now these points are all the same. This disorder is all the same because this is Floquet dynamics, this is time, but space is IID. So now I can do disorder averaging over space. Each point is independent, and I can define a transfer matrix. This transfer matrix is expectation value of a unitary. This column now is unitary because of dual unitarity. Now here I did one more step, which is the folding of the circuit back on itself. So that's why I introduced this thermophile double representation or folded representation, where now, well, I guess most of you have seen this trick in one way or another. So, or if you want super operator representation of the dynamics, but now there is no operator to propagate, it's just 2 times trace, right? Trace modulo square, but still it's useful because when you do the expectation value, when you average, then you couple these 2 copies. There are 2 replicas which are coupled through the expectation value to the averaging over the disorder. Now this is the transfer matrix. Sorry, this is the transfer matrix. You have now is power of this transfer matrix to power L. Now this is system size L. So when you go to thermodynamic limit, then you just have to count the leading eigenvalue, the multiplicity of the leading eigenvalue, which is 1 in this case, and you have to prove that there is a gap. If you show that, then you have proven that spectral form factor has a ramp. Namely, why? Because the multiplicity of eigenvalue 1 is related to the translation invariance in time. So this object is translation invariant in time, so you can show that it has to have default degenerate leading eigenvector of eigenvalue 1. Okay, I mean, this is of course going beyond the idea of this seminar, so I will not go into detail of how to prove that, But again, I mean, there is a very kind of, exciting method, let's say, how to show these things, which we developed. I mean, preliminaries of this method were in this PRL of 2018, but kind of the full-fledged proofs were in this CMP of last year, together with Bruno and Pavel. And the idea is, again, to formulate this problem of computing the degeneracy of this eigenvalue 1 of transfer matrix in terms of solving an algebraic problem that is computing the dimension of the commutant of a set of operators. Now, these operators are defined on spin chain of size t. Now, because we do this space-time flip, now we basically look at spin chain of size t, where t is the time. And now we look at all possible magnetizations, which are defined on the translation invariant chain of size t, and interactions. These are simply components of magnetization. These are all possible interactions. And now you ask, what is the dimension of the set of operators which simultaneously commute with these beasts? And we have shown that these are only translations and powers of translations. So there are t translations and powers of translations which are independent. This gives you the dimension of this commutant. So, of course, this is easy to show. Translations and powers of translations commute with these guys, but the crux of the proof is to show that there is no other. It's easy to find the minimal set, but to find that this set is also maximal is the crux of the proof. Okay, so now, yeah, I think I will have to speed up a little bit. So this was kind of, I would say, the main thing, because it really shows the connection to random matrix theory. Now I will just glance through the rest of the results, which are in some sense weaker, but they are closer connected to physics. I mean, you might think, okay, why should I care so much about spectral statistics? It's a very academic question. I agree. So let's think of physics now. I mean, in physics, it's much more interesting, for example, of local observables. For example, objects like this. You take a local operator, you propagate it with forward and backward evolution, like doing with in the Heisenberg picture. You overlap it with another operator and take the trace. In Floquet systems, which are chaotic, you expect that the tracial state is the only translation invariant state in time. Since maybe you assume there is no other conserved quantity, so this is the only invariant state. So this is the only meaningful equilibrium correlation function, which now depends on the distance between x and y and depends on time. And it turns out that this correlation function can be computed very easily for dual unitary circuits because of the virtue of dual unitarity. So, I mean, I will just give you the intuitive reason for that. Again, it's very easy to show, but it becomes too technical for the talk. But the intuitive statement is that now we have dual unitarity, which means we have causality, which means causality means that the correlations, quantum correlations, can only propagate within light cone, which opens at speed 1 from an operator, right? You place an operator somewhere, and then correlations can only spread in this cone, which opens at this A beta and goes upwards. But now we have a dual unitary system, which means you can also rotate for 90 degrees. And so then correlations only spread in this pyramid, in this light cone, which opens in space. So which means that correlations in dual unitary system can only propagate in the intersection of two light cones, which is the light rays, which move with speed plus or minus 1, depending on the parity of the initial operator, right? There is these two sublattices. Depending on the parity, these two operators should be on the same line. For example, this is the only non-zero operator, only non-zero correlation starting from operator A beta here, which is with the operator which is in the same light ray starting at A beta. And using that, you can compute this correlation function. Now we can simplify the circuit. Assuming that all the other correlators are 0, we can simplify this correlator. We can just use unitarity to prune everything away, which is outside the cone. And then we use dual unitarity, which means we connect these wires. And then we kill everything else. So what you get is this. But this is just iteration of what is known in quantum information theory as unital completely positive maps. So now this is just like you start with the operator A beta, you apply an super operator, you get this operator, you apply another times the same super operator, you get this one, you apply it 2t times, you get the whole thing here, you compose it with A beta, or you multiply it with A alpha, sorry, you take the trace. So that is just what is written here. It's just application of a completely positive unital map, either M plus or M minus, depending on whether initial operator is an even and odd or odd sublattice, and you get the full correlation function. So the only non-zero correlation function is described by C plus or C minus, where x minus y is either t or t. And then, of course, everything is now in the spectrum of this completely positive unitary dynamics. Okay, now I will skip this. I mean, I will go just flash through it, but just considering the spectrum, the eigenvalues of these completely positive maps, which have to be inside unit disk. I mean, these maps have to be non-expanding. So there is the one eigenvalue 1, which is associated to unit operator because these maps are unital. But then the rest of the spectrum can either be strictly inside unit disk or on the unit circle. And depending on that, you can have either non-interacting dynamics, non-ergodic dynamics, ergodic but non-mixing, if some eigenvalues on unit circle but not at 1, or ergodic and mixing if all the non-trivial spectrum is inside unit disk. So this is what now I would call ergodic and mixing. So that's something that now goes back to my first slide. That's the analog of an example of mixing in cat maps. Now we have it for a many-body system, which is very nicely ergodic, so that each other spin is a perfect reservoir for the target spin. So the system behaves like a perfect reservoir to its target spins. So you can describe dynamics of a target spin as a single qubit quantum channel. And that's all rigorous. Okay, so now there are a couple of other results, but again, I have to soon close, so I will just really glance through them. That we can solve, for example, non-equilibrium quench problem, I mean local quench problem for the dual unitary dynamics, for which we have to also put particular constraint of the initial state. For example, you start from an initial state, which is an MPS, but this MPS, which is described schematically like this, but this MPS has to satisfy a particular condition, which is kind of analog of dual unitarity for the initial state. And then you can compute this object, which is a thermodynamic limit of a finite time quench of a local operator, which you place somewhere in the middle of the chain. And this is just written in terms of then a transfer matrix, a space transfer matrix, which is a dashed region here, which you iterate. And again, reduce to computing the leading eigenvector. Okay, this was actually the work which was essentially done by Lorenzo Piroli. Now I have some problem with this progress of slides. I'm not sure why. Okay, I think, yeah, then there's been many other results, but I think I should close. So I should just give you some intuitive ideas for the rest of my talk. So there are other objects which we can compute, for example, objects related to operator entanglement entropies or entropies of operators treated as states, as superstates in tensor product space. Particular compute simplest Renyi entropy, like Renyi 2 entropy in terms of multi-replica objects, and then using dual unitarity. And then there are many other, recently there has been many other papers building on similar ideas, but maybe loosening up some of the assumptions that we do. For example, you can still use this space-time flip, but not assume unitarity of space dynamics, right? You can consider general many-body dynamics using similar ideas, and you can still get interesting results. These results are essentially, they are not rigorous. I mean, you cannot prove stuff, but you can get interesting results. I mean, like there's been discussions again of in Oxford group of many-body localization, possible interpretation of many-body localization as symmetry breaking in terms of this space dynamics eigenvectors, the so-called spectral Lyapunov exponents. And then a group of Vedika Kemani has considered measurement phase transitions as space-time duals of some interesting transfer matrices. Dima Abanin has a formulation in terms of what he calls influence functional, which is just the leading eigenvector of space dynamics. And also we had a paper which I wanted to briefly cover, but there is no time, which shows somehow how to go beyond dual unitarity in perturbative fashion. I will not go into that because it's time, so I will close, but I will just try to go to the conclusion and try to just describe what I mean by that. So I'm sorry for the last couple of slides, which I was not able to cover, but it's always like that. So of course, I told you about some line of research which allows someone to prove some statements about a relationship to random matrix theory and exact computation of correlation functions in interacting quantum systems of particular sort. The question is, how special are these systems? And this is a natural question. And then I again go back maybe this is just wishful thinking, but then I can go back to my kind of history, to the way I learned physics, and I dig up textbooks in dynamical systems, and then they teach me that hyperbolic dynamics is structurally stable. So if I take a strongly chaotic system like CatMap, even though it's linear, it's structurally stable. If I shake it a little bit, mathematics can prove that topology of dynamics doesn't change. So there is the same structure of periodic orbits and Kolmogorov-Sinai entropy and all that. This is kind of robust. I mean, it's just perturbatively changing. So now this is what maybe we want to do here now. Now we have these solved ergodic points of many body systems, and we like to shake them a little bit, introduce perturbations. And in some specific situations, we can prove that these perturbations, these systems are stable against perturbations. For example, correlation functions can be still computed perturbatively. This is very different from what people find in integrable or free systems. When you integrable system, where you shake free system, you immediately go. I mean, the exact solution immediately goes, and physics become completely different, right? So here, the hope is that this physics could be robust against perturbation. That's the main reason why I'm excited about it. So, and then the main challenges for future work on these lines. These are all results. Again, I mean, as you have seen, my emphasis was now on results which you can show exactly or prove. So, of course, you can use similar methods to progress in more intuitive ways, but still we would like to have something that we can control exactly. And the question is, what can you do when you have finite systems? Of course, you know that finite systems are always a problem. And here is also the problem. I mean, all these methods work in thermodynamic limit, but the question is, can we make systematic progress in finite systems? In particular, why we would like to do that, for example, we would like to have some simple fine-tuned interacting systems for which one can prove, for example, eigenstate thermalization. So if you want to address eigenstates, you have to control finite systems. But then, of course, these nice tricks that I have described don't really work, or at least have to be somehow adjusted, and we don't know how. So this is like interesting questions for future. So I think with this, I would like to close. Thank you.
Thank you very much for the talk. So now it's time for questions, and I ask people in the chat and in the room to raise their hands, and then we'll try to proceed with some order. Maybe I use my prerogative as a chair to ask a quick question, which is about this dual unitarity condition, which I found very intriguing, because on the one hand, it reminds me a little bit, if I think of a continuum system like a 1+1 quantum field theory, it reminds me a little bit as requiring that the dynamics in the theory and the dynamics in a theory where I exchange space and time by some double Wick rotation, like people do sometimes in mirror models for integrable theories, that they are both unitary. And it also reminds me a bit of modular transformations for a conformal field theory. But on the other hand, it seems that it's a little bit different maybe in nature and a little bit more spatial. So I was wondering whether you could comment on, for instance, what could be the continuum limit of this property, how I could think of it.
Yeah, that's an excellent question. It's quite puzzling. I don't think there is a continuum limit, which makes sense. For example, you cannot smoothly connect this to Hamiltonian dynamics, because you know, there is this simple, in the Teasing model, for example, these coupling parameters have to be pi/4. So if you want to consider this as a trotterization of a continuous time Ising model, then this you cannot, I mean, you cannot satisfy that. I mean, or in other ways, I mean, if you use Trotter formula, then your 2-qubit gates have to go close to identity. But identity is as far as possible from dual unitary, because the dual of identity is projector. If you look, identity would be just like 2 wires upwards. But if you look at sideways, it's just projector. So that's kind of intriguing, because that means that if you want to connect this to field theory, then this is at the same time Euclidean and real-time dynamics. I mean, it's symmetric with respect to space-time flip, like Euclidean field theory, but it is real-time. You don't do really Wick rotation. So, and the reason why it can be so puzzling is that it's not smoothly connected to continuum. So, Yeah, I mean, I cannot say more, but it's kind of, I mean,
no, thank you. That's very interesting. So I think there is one question in chat, and then after that, maybe if there are questions in the room, somebody can take care of giving a microphone. But first, the question in chat. Some data, please.
Yeah, so my question is, like, as far as I can understand, all these systems for which you are showing behavior like random matrix statistics are all numerically simulated systems, right?
can you repeat the last sentence?
Numerically simulated systems. I mean, all these systems are numerical simulations.
Yes.
So is there, has there been any experimentally, I mean, any experimental setup which kind of gives rise to these random matrix statistics?
That's a good question.
Yeah.
There has been experimental simulation of correlation functions for kick-teasing chain, for self-dual kick-teasing model. I mean, last year there was a paper by people working with Honeywell quantum simulator, and they reported simulation of correlation functions using this dual-unitary circuit, which simulates kick-teasing models. So that's like a nice benchmark, for example, for experiments on quantum simulation. But to experimentally address this level statistics, this is maybe, I don't know if this is really a good, well, level statistics directly, I think it's a huge beast. I mean, you have exponential many levels. Why do you want to measure them? I mean, but if you just want to measure spectral form factor, that's probably something that could be done. I mean, so for example, at short times, this should be very sensitive to chaos and or integrability.
No, for instance, the way Wigner derived his result was looking at the nuclear energy levels. So I'm just wondering if there's anything similar in condensed matter systems where you can get the energy levels of some system which you can relate to this kind of statistics.
Yeah, I mean, if you can measure energy spectrum of a system of 10 qubits, it's 1,000 levels, then you can compute that. But I don't really see good motivation to do that. I mean,
well, the motivation is, I mean, unless you make contact with nature, it's still only mathematical theory, right? I mean,
yeah, okay, yeah, I agree.
Yeah.
So maybe if there are any questions in the room, please go ahead.
Other questions? No, seems that all the audience is satisfied. Other questions in the chat?
So I don't see any other question now in the chat.
Okay.
So maybe then in view of time, and I'm sure that people in Florence will want to enjoy the nice evening and maybe get some nice dinner. So I think it's a good moment to thank again Tomaz for the nice talk and everybody who took part.
Thank you. Bye.